as said, my talk today is based on this paper that we put out in February earlier this year with Luca Delacretaz and Gabriel Cuomo on the large charge sector of 3D parity-violating CFTs. We're specifically going to focus on 3 dimensions and for large U1 charge. Luckily, because this is a very expert audience, I won't have to go through much of an introduction. So I'll mainly start out with directly diving into the EFT after just talking very briefly about some of the salient features of the general construction that would be relevant in our case, talk about what parity violating terms that we can add to the EFT and their consequences for large charge operators, the spectrum, the OPE coefficients, and in particular, how they're different from the case with parity in that when we put this theory on a sphere, we'll see that we're forced to have vortices. So that will be the first part of my talk. And because I have about 25 minutes, I'll try and run through this very briefly and mention key results and give a rough intuition for how to obtain them without going into too many details. And then in the second part, I'll mention a very specific example where we realize the predictions of this EFT in what we're calling Anyon Superfluids. This is one of the few examples where this EFT can sort of be explicitly derived, at least to leading order on a plane. I'll show how that can be done. The charged operators here are going to be monopole operators, so I'll discuss that and the potential existence of a double scaling limit. I'll talk about what exactly these vortices that I mentioned on a sphere look like in this theory, and also talk a little bit about going beyond the EFT approach and what else can we see in this theory. And please feel free to stop me at any point to ask questions. Okay, so to begin with, just a quick review of the large charge EFT for U1. The EFT is supposed to be that of a superfluid with a leading term given by this, where phi is a compact scalar. Any other subleading terms that are that preserve parity come at 2 derivatives, are suppressed by 2 derivatives compared to this leading term. One can also rewrite the same theory in a dualized language by treating by replacing this compact scalar phi by a U1 gauge field. Oops. The U1 gauge and the action now looks like this: mod f, where mod f is square root of f mu nu to the 3/2. I want to mention briefly the symmetries that this EFT has and the currents associated with it. The first one is a zero form U1 symmetry, which is the ordinary U1 symmetry that you see in a superfluid, whose current in the phi language is just the gradient of phi with an appropriate normalization. I have ignored any overall factors in these expressions, so these are not exact expressions. In this dual language, this U1 symmetry is going to be topological. In particular, its current is identically conserved off shell. On the other hand, we also have a one-form symmetry, which counts the winding numbers of the superfluid. In this phi language, this one-form symmetry is identically, the current is identically conserved off shell, but in the dual language, this becomes an on-shell statement. And the reason we work with this dual language in particular is because this zero form symmetry is fundamental to the EFT, but the one form symmetry is not and can be broken. So we want to be able to break it easily, which is hard to do in terms of in this phi language, because the symmetry is just conserved off shell. And we'll see how it becomes easier.
Quick question.
Mm-hmm.
So
yeah,
the upper left-hand box, are you sure it's not supposed to be grad phi to the 1? Times grad.
Oh, yes, you are right. Sorry, that is a typo here. It should be grad phi to the 1. Thank you.
Okay.
Yeah. And of course, this theory was originally developed in these papers by many of the authors are here. Okay, so moving on. Now we allow ourselves to let go of parity and use epsilons in the action and try and think of what possible terms we can add. And this is a question that had been answered all the way back in 2014 in this paper by Goldstone, Roberts, and Son. And in principle, there are two parity odd terms that one can add. One of them that's here is called the Euler term. The other one becomes a total derivative in the conformal case, but it's non-trivial for non-conformal theories. So we're going to ignore it because we want to put a theory on a sphere. This Euler current is called an Euler current because its density, when integrated over space, gives the Euler characteristic of the manifold. So it's sort of a topological current. It is also identically conserved because when you take the derivative, the divergence of this Euler current, you get a scalar triple product of three vectors in a plane, which are gradients of u, which are all orthogonal to this velocity u, and therefore its divergence identically vanishes. So because of the fact that this Euler current, I should mention this parity violating term is only one derivative subleading compared to this leading term, as opposed to the other two parity even corrections that would be at order del squared. The reason it's one derivative is because f has zero derivatives, therefore a has -1 derivative. So this a cancels one of the two derivatives going into the expression in the Euler current. Okay. So because the density of the Euler current gives the Euler characteristic when integrated over space, that means that under large gauge transformations, kappa has to be quantized in order for the exponent of the action to be single valued. So kappa is going to be an integer. Another characteristic of this term is that kappa controls something that is called the Hall viscosity in condensed matter. On the condensed matter side of things, in particular, if you put this on a manifold with a fluctuating time-dependent metric, the stress tensor will respond to the time derivative of the metric with a parity odd response that is called a Hall viscosity. One way to think about it is that if you have some sort of object placed in a fluid that has Hall viscosity, rotating the object will create pressure in the fluid, either radially away from the object or radially inward, which is why it's a parity odd term. And in particular, this Euler term breaks the one form symmetry because of this explicit A, under which, under the one form symmetry, A shifts by a constant vector. Therefore, this is not invariant. Now, this makes it clear why this term is cannot really be seen in the phi language, because you really can't break this one form symmetry in the phi language. The equation of motion for this theory is simply the non-conservation of this one form current. The divergence of the one form current is then given by the Euler current with a factor of kappa. Okay, now let's put this theory on a sphere. So if we take the time component of this equation of motion and integrate it over space, we find a contradiction immediately. The left-hand side is a divergence, so its integral is 0. The right-hand side is proportional to the Euler characteristic of a sphere, which is 2. So this is kappa, which means that this can't really be the full story when we put it on a sphere. What that means is that when we want to put this theory on a sphere, we're automatically forced to include vortices, which in the dual language are point charges. So we do so by adding Wilson lines to the action. Any self-interaction or dynamics of the Wilson lines are going to be subleading. So hence these triple dots. The angular momentum of each vortex is in fact proportional to its location when embedded in R3 with a coefficient, a prefactor of half the total charge. And we also have Coulomb interaction between these vortices, which is this logarithmic, which gives a logarithmic correction to the energy. Okay, so the ground state of this theory on a sphere, which corresponds to the operator of minimum dimension for this given large charge, has to have vortices. And the fact that it has vortices means that there's going to be a correction to the energy. The energy of this ground state can simply be obtained by minimizing the energy of this configuration of vortices. This is in the math literature known as White's problem, and there's in general no solution except for some special cases with kappa equal to the following. Kappa, I forgot to mention, kappa is the number of vortices on the sphere. For references on this, you can look at the references in this paper. But there is one thing that's known very well, which is a theorem that the center of mass of this configuration of point charges on the sphere is at the origin when kappa is not equal to 1. When kappa is equal to 1, the center of mass is obviously going to be where that vortex is. So kappa equals 1 is sort of an exotic configuration, which we don't really expect to see very often in realistic theories. So our main result for this classical ground state is that the lightest operator has spin 0 for kappa not equal to 1, and spin q/2 for kappa equal to 1. And the scaling dimension of this operator picks up a square root q log q correction from the fugacity and the self-interaction of the vortices. And this correction is proportional specifically to this parity odd coefficient. Any other correction that comes from subleading terms in particular is going to be smaller than square root q log q. But there's something a little strange about this, which is that because we're considering a sort of classical configuration, our ground state becomes inhomogeneous because of the presence of vortices and has a large degeneracy which corresponds to the rotation of the state. I should also say in our case, so this other paper in 2017 also discussed vortex configurations for charged operators with a finite spin. There they had, for instance, a vortex anti-vortex pair getting created, but that is very different from our case because that was sort of an excited state on top of the minimum scaling dimension operator with a finite spin. Here we're saying that for our ground state, and in fact for spin equals 0, we are forced to have vortices. Okay, so how do we think about this sort of large degeneracy and inhomogeneity of this ground state? And the answer to that is that we quantize the theory. The classical answer is not accurate. And in fact, when we quantize this theory, we want charged particles in the presence of this background magnetic flux. We get Landau levels on the sphere, and this lifts this large degeneracy. In particular, for example, for kappa equals 2, we can exactly solve this problem. And the operator with the lowest charge, the lowest scaling dimension for a fixed charge and spin has this form. So where delta min q is the scaling dimension of the operator with 0 spin. And any non-zero j corresponds to vortex excitations in the sphere. So these vortices start fluctuating, pick up some spin, and this increases their energy slightly. But note in particular that this jj+1 factor is suppressed by a very large number, which is q, which is the largest scale in our theory. Contrast this with the phonon excitations that you would get in the superfluid, which have a difference of square root jj+1/2 without this suppression. So these vortex excitations are much, much softer than the phonon excitations. And unlike the parity even case, we now have 2 branches of operators coming out of this delta min q. Another thing we can look at from this are the OPE coefficients of operators, and the signature of the parity odd term here is going to be, as I mentioned before, in the Hall viscosity. The Hall viscosity, you can see from these papers that there's a Cuomo formula for it, which essentially relates it to a 4-point function of the stress tensor with this large charge operator. So it's sort of like a charge analog of these heavy, light 4-point functions. The stress tensor in particular is going to be linear in fluctuations of the Goldstone mode. It sort of schematically looks like this, where this kappa term is one derivative suppressed compared to the C1 term. Therefore, we can expect that after putting in a sum over states in between here, that this parity odd signature will be found in 3-point functions of this type, where Q prime is Q plus some single phonon. The reason the single phonon state will have the signature is because the stress tensor is linear in pi. And indeed, when we compute this, where Qj is a single phonon state with spin j, we find the following scaling of the OPE coefficients with C1, Q, kappa, and j. Okay, so switching gears a little bit, let's talk about what candidate theories can this EFT be used to describe. The immediate answer that comes to mind would be Chern-Simons matter theories, either the UN or the SUN type, which are the most commonly used ones because of their bosonization, post-Fermi dualities. They do have a global U1. The UN theories have a global topological U1, which corresponds to the current built out of the U1 factor of UN. And the SUN ones have a fermion number current. However, these theories seem to be Fermi liquids at the strict infinite n limit, based on these papers from 2015 and 2020. But it's possible that they become superfluids for finite n due to perhaps a proliferation of diagrams at order 1 over n, because everything is being put at finite chemical potential. Perturbation theory is a little more involved. So while this is in principle something that can possibly be checked, it's too technical, and we'll look instead at an opposite limit, which is n equals 1. For n equals 1, this theory is completely trivial, so we can discard this. We look at U1, and then there's only a single level K. And we take that to infinity to get a perturbative handle for this weakly coupled theory. A non-relativistic analog of this has been studied extensively in condensed matter literature and goes by the name of Anyon Superfluids, which already gives you a hint that when we put this at finite chemical potential, it is going to be a superfluid. For instance, it was studied in these papers earlier. So the theory that we are calling Anyon Superfluids is U1 level K Chern-Simons matter theories with the following action. So we have a single Dirac fermion coupled to a level K U1 Chern-Simons gauge field. There's a global U1 current whose charge corresponds to the magnetic flux density, or B over 2 pi. This theory has a Gauss's law, which is going to be an operator equation on physical states. And Gauss's law basically states that the number of fermions is K times the magnetic flux density. What this means is that if you set this gauge field to some background value for some fixed magnetic field in a mean field approximation, we have K fully filled Landau levels. And the K plus 1 at Landau level is completely empty. And the gap between them is given by square root B over K, which is going to be the cutoff for our EFT. Because this is a system where we have K fully filled Landau levels, it forms an integer quantum Hall state which has an Hall conductivity given by K as well. Now this gap allows us to integrate out the fermions. Because these fermions have Hall conductivity K, this generates a level K Chern-Simons term with the opposite sign compared to what was in the microscopic action. This Chern-Simons term now cancels the Chern-Simons term that existed in the microscopic action, but also generates higher order terms with higher derivatives or higher or cubic terms, etc. So we find that this effective theory now has an action that looks like E squared minus B squared, which is basically the linearization of mod F to the 3/2. So we have, in effect, approximately derived the leading order term in the EFT just by integrating out fermions. And we can read off the first coefficient C1 from this as 1 over 2 pi KQ. Note that because K is large, C1, which is the stiffness of the superfluid, is very small. So when we put this on a sphere, what operators do we expect to see? What operators do we expect to be realized as the operators with lower scaling dimension at fixed charge? And these are the monopole operators. Obviously, because the U1 charge density is the magnetic flux, so therefore the operators just have to be monopole operators. The operator dimension can be computed from the EFT, which is the limit where K is very large compared to 1, but it's also much smaller than Q because we need Q to be the largest scale in our theory. And this scaling dimension is just obtained just by plugging in the value of C1 from the previous slide, and it's given by KQ to the 3/2. There are two corrections to this. One comes from higher loops, which come with a factor of 1 over K, and the other one comes from higher derivatives, which comes from K over Q. One can also compute the scaling dimension of these operators in the opposite limit, where Q is much smaller than K, as was done in these papers. And there we also find the exact same expression. And this is weird because like two opposite limits of the same quantity have the exact same expression. And the reason this is true is because, in fact, there exists a double scaling limit where we take both Q and K to infinity, but fix Q over K. The way to compute this scaling dimension is to organize all the Dirac particles in Landau levels obtained from the monopole background at leading order. And then we can show exactly up to 1 over K corrections that the scaling dimension is indeed this. So this expression up to 1 over K corrections is exact in Q over K. So we basically got rid of this dependence. Okay, so now we want to put these superfluids on the sphere and look at, sort of think about what these vortices could possibly be, where they can come from. And as before, we still have K times Q Dirac fermions that populate sphere Landau levels. But sphere Landau levels are different from planar Landau levels, in particular, that the degeneracy of the Landau levels on a sphere is not just Q, it's given by Q plus 2 mod P, where P is this integer that labels the Landau levels. So K fully full Landau levels requires this number of fermions, but we only have KQ, and we're missing these additional ones. So when we populate these Landau levels, we have K times K plus 1 holes, which are the superfluid vortices. So in this example, we sort of have a very clear realization of why we need vortices, just because we simply don't have enough Dirac fermions to populate all the last Landau level. We're left with a certain number of holes. And in particular, in this example, we have some more information about the microscopic structure of the vortices as well, which we wouldn't in the EFT, in that these vortices here are fermionic. So each one of them would carry an additional spin half. So we can now identify the second coefficient as well, kappa as KK plus 1, which is, again, much larger than 1. So this is sort of an opposite limit where kappa is very large. So we have a large number of vortices on the sphere, effectively forming a vortex lattice. And in principle, we can also work out an effective theory for this vortex lattice, which is slightly different from the EFT for the superfluid with vortices. Note that here I've assumed that K squared, which is approximately KK plus 1, is less than Q, so that we still have K fully filled Landau levels in order to cancel K filled Landau levels in order to cancel the Chern-Simons term. But as it turns out, we can sort of push this a little bit further and look at the other limit, where K squared is larger than Q. Therefore, the last Landau level will be completely emptied, and the holes will sort of spill over into the previous Landau level. In this case, this is beyond the EFT because the Chern-Simons term doesn't indeed get canceled. But instead of the EFT, now we have a number of filled Landau levels is given by, in this diagram, it's K minus 1, but in general, it'll be K minus the floor function of K squared over Q, which is the number of Landau levels that are unpopulated. Now integrating out the Dirac fermion leaves a residual Chern-Simons term, and we can still say that this theory is still described by an alternate EFT, which I'll call EFT prime, which has the following action. So just the EFT action with a subtracted Chern-Simons term. Note that now kappa and the number of vortices are not the same anymore. The number of vortices instead is given by K squared minus this correction. And this changes the coefficient of the subleading term in the scaling dimension from kappa to n vortices. So it's a slightly different prediction for this specific theory. This Chern-Simons term is slightly weird because it causes the superfluid phonons to get gapped. The mass of the phonon is given by square root of k over rho, but this is still much smaller than the inverse of the sphere radius. So as long as we're on the sphere, this gap is invisible, so we can still sort of treat this as a superfluid. Okay, so before ending, I sort of want to mention a little bit about going even beyond this EFT cutoff. This is going to be slightly speculative, so apologies if this is not very precise. But basically, the fact that we have these higher Landau levels in these Anyon superfluids means that the cutoff scale for this EFT, as I mentioned before, is the cyclotron frequency, square root of rho over k. This cutoff scale is also applicable to the EFT prime, at which point particle hole excitations start factoring in. These are gapped, and they sort of break the superfluidity of our theory. However, we still have some analytical control over these particle hole excitations. In particular, if we're working in flat space, we can compute the spectrum of these particle hole excitations beyond EFT using an approach where at weak coupling, where you think of this as a Fermi surface for the fermions coupled to a fluctuating gauge field. This approach was developed by Sun for applications, Sun and collaborators for applications to quantum Hall physics, and this spectrum is picked up from this paper. So these higher particle hole excited states are interesting because they're essentially distorted Landau levels. Note that they end and begin at the same Landau level. And an interesting question to ask would be, what do these states correspond to as operators in the CFT? We still have to put this on the sphere, which might be a little bit subtle. One very curious thing about these states is that if you look at there's a dispersion relation at low momentum, these states have higher spin. The second Landau level has spin 2, the third Landau level has spin 3, the fourth one has spin 4, etc. So it seems indicative that there might be some higher spin operators in this theory that we're missing, similar to how in the infinite n limit for large n Chern-Simons matter theories, there do exist these higher spin currents. And with that, I will end my talk since I'm out of time. Thank you.
Wow, very interesting stuff. Are there questions? Questions for the speaker? Well, I have a question. So if you were to quantize the theory on some other spatial slice other than the sphere, the number of vortices is proportional to a topological number of the spatial slice, like the Euler number or something?
Yes, it's in fact exactly this kappa times the Euler characteristic divided by d.
I see. Yeah, sorry, I didn't notice that. Oh, that's interesting. So if you took like a very high genus Riemann surface or something,
right,
could you make the vortices get very dense, get into some new regime that way?
Yes. So in fact, even on the sphere, if you take kappa being very large, you get like a vortex lattice on top of this superfluid. And in our paper, we have a sort of effective description that we picked up from another paper that generates an EFT for vortex lattices. And even there, we still have these two regimes of spectra, with one being the phonon excitations and the other being lattice excitations.
That's interesting. I guess my other question is, so I guess there are some, I don't remember the taxonomy very well, but I think there's supposed to be some like Chern-Simons matter theories with like non-generic global symmetries. Like I guess even the SU2 bosonic Chern-Simons matter has an enhanced SO4 or something like that. Sorry, I guess there's a global SU2 in addition to the gauge SU2. I guess Watanabe had a paper with working out that large charge limit, but I'm not sure the effective theory was ever worked out. Would you expect it to be a different effective theory? Do we have any idea what the effective theory might be like for the case where the UN gets enhanced to a global SU2?
That's an interesting question, and I'm not exactly sure because our approach explicitly relies on the fact that the global symmetry is specifically U1, so that we can dualize to write this Euler term. So I'm not sure what it would look like for non-abelian global symmetries.
No, thank you.
But would it change anything if the global symmetry is SU2 or something, SO3 maybe, but you just turn on the chemical potential for the one generator?
I see.
No, I don't know.
I mean, it doesn't look obvious how to do the dualization, even if
no, I agree with
preserves the SU2 manifestly.
Yeah.